Welcome back to Structural Dynamics. In this lecture, we are going to discuss regarding the Hamilton principle. Okay. Before going to see this Hamilton principle, we will see some basic parameters like work done, which are influence the Hamilton principle. Okay. So I am moving to work done. That is nothing but virtual work done in your body. So we will see principle of virtual displacement. What is the virtual displacement? If a system which is in equilibrium under the action of set of externally applied forces is subjected to virtual displacement, that is nothing but a displacement pattern compatible with the system's constraints, that system constraints, the total work done by the set of forces will be zero. When a body in equilibrium, when we apply the load over that particular body, the body will be displaced from one location to another location. Or we can see in a beams, when we apply the load over that particular beam, then body will be deflects in downward direction. That deflection we can see as vertical deflection. Okay, that one we used to call as the vertical displacement of the body when we apply the load. Okay, similarly during the earthquake also we can see this type of displacements of the body. When we apply the load in one direction, the displacement of the body will be happens in opposite direction. Okay, there will be some constraints will be there, means conditions will be there. Depending on those conditions we used to find total work done by the body. If you apply one load, you can get one displacement. If you apply number of forces, then we can see number displacements. Okay, each load will having the different displacement in their own direction, a load applied direction, that is called as the vertical direction. And that particular work done, the force and displacement, the load into displacement, we used to call as the work done. Okay, work done of the body. When you apply the external load, that will gives external work done. Okay, the load which we apply over the body, and the deflection or displacement of the body, the product of these two we used to call as the work done, externally work done. The work done which is the displacement which is happened due to the externally applied load, we used to call as the external work done. Okay, the virtual work principle requires that the external virtual work WE of T performed by the external loading acting through their corresponding virtual displacements be equated to the internal virtual work done. If you see that the external work done means, we used to call all the loads into displacement of individual load and individual vertical displacement, we used to get one work done of the body. For each load we used to calculate total work done of external load. And similarly, the body which is resist this total work, this total loads and displacement, that one we used to call as the internal work done. The body which resist all these external loads, those loads will be and the displacement will be overcome by this material, we used to call as the internal work done. When we equate these two equations, okay, internal and external work done, the total work done will become zero. Means external work done will be equal to the internal work done always. Okay, external work done is equal to the internal work done. When if you see here, del WE is nothing but external work done, and which is equal to the del WI internal work done. Okay, based on this particular equation, this principle, we used to derive the Hamilton principle. Regarding Hamilton principle, just consider mass particle m shown in figure. If you see here, this is a mass particle which moves in response to the applied force vector. Okay, this will move with respect to the applied force. That force will be sum of the unit vector. If you see here, f of t is equal to fx of t into I, fy of t into j, fz of t into k. Okay, if you see this force vector, the force may be in any one direction. Okay, because of this force, this can be moved in its real path. Okay, because of this force it can be moves in real path. If you see there, this one is the solid line indicates the solid curve indicates the real path of the body. And when we apply the load or force over this body will be moves along the path, and it moves to the point 1 at time t1, if you see here. And when we apply force further, it can move point 2 with a time duration of t2. Okay, if you can, if you consider a mass, the real path will be like this. Okay, but there may be a varied path which indicates the, and we use this coordinate system x, y, z, whereas r of t indicates the resultant of this force, and del r of t is indicates the resultant total displacement of the particle from its original position to displaced position, when we apply the forces in all direction. Okay, whereas externally applied load we used to take as P of t, the structural resistance, Fs of t, resistance offered by the body. Externally applied load is P of t, and the damping resistance, the dampness offered by the material we used to take as Fd of t. By D'Alembert's principle, it is equilibrated by the initial resistance Fi of t. Okay, the body which is having initial resistance. Okay, we used to we used to balance with the initial resistance of the body. Okay, with total displacement of the body. If from this figure we can see how to derive the Hamilton principle. Here we used to assume some of the external loads, the work done by external loads is equal to the sum of the internal work done. It means the force which is the work done due to the force which is there due to the external load and internal inertial force will be equal. The force resisted by the inertia, both are will be equal. If you see here, for suppose if you take this element, f of t is the total force which is acting over the mass m, and f of t will be moves in three directions. This force is the f of t is the resultant of these three forces, f of x of t into I plus f of y of t into j plus fz of t into k. Okay, this force can be written as like this. Force in x direction of t, t is the time varying force. Force is not a fixed constant, that is force with respect to time, the varying force with respect to time. And with respect to time, this acceleration of the body, inertial force also changes. Okay, if you see here, x direction force will be there. Due to this x direction force, there will be inertial force will be generated in opposite direction, which is nothing but mass into acceleration in x direction. Okay, and displacement, vertical displacement, virtual displacement, which is there is nothing but del x of t. Okay, this is the total work done in x direction. Similarly, total work done in y direction, Fy of t minus m into acceleration of the body in y direction. This will give inertial force, whereas the f of it is nothing but external force due to the external load. Okay, and sum of these two will be balanced by the vertical displacement in the y direction. Similarly, in z direction, fz of t, which is indicates the force in z direction, and that body will be moves with the acceleration of z of t. Okay, means this one is the acceleration in z direction, mass into acceleration, it will gives inertial force, and this inertial force, some of the forces in x direction into displacement, vertical displacement in that direction will be gives work done. Okay, this is total work done by a body. Here we are considering external loads and internal loads which are there due to the inertial force. Okay, and multiplied with the displacement, vertical displacements. Okay, resultant of these forces should be zero when we apply the Hamilton principle. If you rearrange the terms and integrate this equation from the time domains t1 to the time t2, it will gives like this. Integration of t1 to t2. Here we used to take some of the inertial forces, mass into acceleration into time into dx into t, and similarly acceleration into displacement of the body, and similarly acceleration in z direction into displacement of the body in z direction, and with into dt when we integrate with respect to time. These all are the time varying loads. Okay, these loads vary with respect to time. Okay, and this is the inertial force, whereas the external force is nothing but f of x of t into del xt plus f of y t into del y t and fz of t into del zt, whole multiplication with respect to time dt, which is nothing but equation 1. And in this equation I am dividing I1 as the inertial force, I1 which can be given from this particular term of the equation 1. In the equation 1 we can see the inertial force. That inertial force I am taking as I1, whereas this is time varying function. That's why I am keeping here instead of this total equation. We can see this total inertial force as del t of t into dt, whereas del displacement del of t1 to t2 into t of t into del t, and this equation can be written as like this. T of t is the kinematic energy of the particle given by like this, whereas kinematic energy is nothing but half of the mass into velocity square. If you see here in this equation, okay, this function, if you integrate that equation, if you integrate this equation, okay, if you integrate this equation first term with respect to t1 and t2, we can get the equation like this. T of t is equal to half of m into velocity square into yt square. Velocities in three direction, we can see z square, z direction, velocity in x direction and y direction. Okay, sum of these forces, sum of these velocities into half into m, which can gives the kinetic energy. Okay, and separate the force vectors, whereas some there also we have force vectors here. Okay, second term indicates the force vector here, and that force vector we can write as f of t is equal to fc of t plus fnc of t, whereas fc of t indicates the conservative force, whereas the non-conservative components will be fnc of t. And potential energy can be developed in this body. That potential energy we used to take as v velocity in the function of x, y, z directions with respect to time. Okay, is then defined such that conservation force fc of t will be defined as like this, whereas force in x direction, conservative force in x direction, del v by del x of x y t of into t is equal, which is nothing but force in x direction of conservative of t, and second one is okay, which is nothing but minus fy of here if you see velocity function, okay, velocity of the body in x, y or z direction with respect to dy del y. Okay, del v with respect to del y, it will gives force in y direction. Similarly, velocity in z direction, del v by equation, velocity equation by del z, this one gives force in z direction. These all are the conservative forces. Okay, making use of the equation, not equation, this equation 1, 2 and 3. By using these equations, equation 1, equation 2, this is not one, actually this is equation 2. Okay, by using equation 1 and equation 2, and 3, we can define the second second term of the equation 1, whereas I2 is nothing but integration of this is sum of this conservative force and sum of non-conservative forces. Okay, the work done by conservative force and the work done by non-conservative forces. Okay, I2 will be indicated with this equation. After applying I1 and I2 in this those two equations, we can get final equation like this. Integration of T1 to T2 of del of capital T of T minus V of T into del dt is the one function plus integration of T1 to T2 with non-conservative work done with respect to dt. We can get this is the total equation for Hamilton principle. The above equation, which is generally known as the Hamilton variational statement of dynamics. Okay, this is regarding the Hamilton principle. With this, I am ending this particular lecture.